Welcome back to the Deep Dive. If you, our expert listener, are anything like us, you spend your time tracking the leading edge of machine learning and data science, knowing that the real measure of progress isn't just theory, it's, well, economic utility.
Exactly.
But the conventional academic benchmarks we typically see, the reasoning tests like GPQA or MMLU, they often feel a bit detached, don't they? Detached from the actual complex real-world value these frontier systems are meant to unlock.
They absolutely do. They test capability in a vacuum, often.
So today we are moving entirely beyond those conventional academic settings. We are diving deep into the source paper, GDPval, evaluating AI model performance on real-world economically valuable tasks.
A really interesting one.
Our mission here is to give you a comprehensive, structured analysis of this GDPval benchmark, look at its extremely rigorous methodology for constructing and grading these tasks.
Which is key.
And, critically, get into the empirical results. How do these frontier models actually stack up in terms of quality, speed, cost benefits on tasks that directly feed into major economic sectors?
That framing is essential, especially for an audience like ours, well-versed in quantitative analysis. Economists, they've long struggled to accurately measure AI's current and future impact.
Right.
Traditional economic metrics, things like looking at enterprise adoption rates or total usage patterns or even just observed GDP growth, these are almost universally lagging indicators.
They tell the story after the fact.
Precisely. Years, maybe even decades after the tech's already been deployed and integrated. GDPval represents a really vital alternative approach. It's a method focused on developing and measuring leading indicators.
Yeah.
It's a direct, attributable measurement of model capability, specifically on high-value work. And that lets us assess economic relevance, potential productivity shifts, well ahead of widespread industrial adoption.
And the scope seems deliberately broad.
Oh, it's vast and deliberate. It covers work activities tracked by the U.S. Bureau of Labor Statistics for 44 occupations across the top 9 sectors, contributing most significantly to U.S. GDP. This strategic breadth is exactly what gives the measurement its economic salience.
Okay, let's unpack this then. The core value proposition of GDPval, it seems, really lies in its realism and its representative breadth, especially when we contrast it with other evaluations out there.
Definitely.
We've had domain-specific benchmarks, sure, but maybe nothing quite capturing this broad, high-value slice of real-world knowledge work like this initial effort attempts. So when we compare GDPval to those popular academic benchmarks, GPQA, MMLU, maybe even HumanEval, the methodological difference, it's fundamentally about purpose, isn't it?
Yes, entirely.
Those tests, they primarily gauge abstract reasoning, maybe knowledge acquisition or simple code completion. GDPval tasks, on the other hand, are derived directly from actual work products, the kind typically created by experienced industry professionals.
Real deliverables.
Exactly. And they aren't validated by a simple correctness score. They're validated by the time, the cost, the quality standards associated with completing them in a professional setting. It really shifts the core question from, can the model pass a test, to something more like, can the model produce a deliverable an expert would actually pay for?
And that commitment to representative breadth, it overcomes the primary limitation of those highly focused evaluations you mentioned.
Like SWD Lancer for software engineering.
Exactly. Excellent for its domain, but limited. GDPval is designed to be domain agnostic. It encompasses 1,320 distinct tasks across 44 occupations. And these were meticulously selected to cover the majority of the work activities tracked by ONET.
That's the Department of Labor's database, right?
That's the one. Their key database for these specific high-value roles.
And the complexity of these tasks, it sounds non-trivial. These aren't just simple text-in, text-out prompts.
Not at all. The benchmark demands long horizon capability and intense multimodality. Models have to successfully manipulate and generate diverse professional file formats.
Like what specifically?
Well, think CAD design files, photos, video, audio, slide decks, large spreadsheets with complex formulas, even synthesizing customer support conversation. Wow. And they also have to manage significant context. Models needed to parse and utilize up to 17 reference files just in the open-sourced gold subset.
17 files for one task.
And in the gold subset, yes. And up to 38 reference files in the full set. That level of information synthesis requires a really robust ability to, focus and manage context over extended conceptual horizons.
Okay, so the tasks are complex. Let's talk about the economic prioritization. How did they choose which tasks, which sectors?
It was remarkably strategic. They zeroed in on 9 specific economic sectors. These include big ones like real estate, manufacturing, professional, scientific, and technical services, healthcare,
Why those 9?
because each of these sectors contributes over 5% to the U.S. GDP, based on Q2 2024 value-added data, so they're economically massive. Collectively, the roles covered within this benchmark represent an aggregate compensation base of roughly $3 trillion annually.
$3 trillion.
Yeah, it immediately grounds the benchmark in tangible, high-value professional labor. There's real money behind these tasks.
Yeah. Okay, so they picked the big sectors. Then how did they narrow it down to the 44 specific occupations within those sectors?
The selection criteria were very focused. They needed roles that were both economically salient and, crucially, inherently compatible with current AI capabilities, or at least the kinds of tasks AI could theoretically do.
Makes sense.
So 2 main criteria. First, the occupation had to be among the top 5 within its sector, contributing most to total wages and compensation.
So high-earning central roles.
Exactly, ensuring they captured economically central roles.
Yeah.
And second, the occupation had to be classified as predominantly digital.
Predominantly digital. How do they define that? That sounds potentially tricky.
It involved a fascinating and pretty nuanced methodology. I think our audience, appreciating systematic data classification, will find this interesting. They leveraged the detailed task-based approach from the ONET database.
Yeah.
For every single discrete task identified within an occupation in ONET, they prompted GPT-4o, a capable model itself, to act as a classifier.
Using AI to classify the tasks for the AI benchmark.
Hey, yeah, a bit meta, but efficient. It classified each task as either digital or non-digital. But crucially, they didn't just count the tasks. That wouldn't be accurate.
Right. Some tasks are more important than others.
Precisely. They weighted the digital classification using ONET's own established metrics: relevance, importance, and frequency scores for each task within the occupation.
So a task done daily and central to the job gets weighted much higher.
Exactly, much higher than some rare marginal task. The final classification rule was pragmatic. If at least 60% of an occupation's weighted component tasks were classified as digital, then the whole occupation was included in GDPval.
And did they validate this approach? Does this digital classification actually line up with how economists think about these things?
It does. And what's important for validating this method is that the paper confirms this digital classification aligns perfectly with established economic task content frameworks. They specifically cite the influential work of Acemoglu and Otter from back in 2011.
Okay, that's a foundational paper.
It is. They observed quantifiable correlations showing that their weighted share of digital tasks increases dramatically alongside non-routine cognitive content.
The kind of thinking work AI is aimed at.
Right. And conversely, it decreases sharply with routine or manual content. So this methodology confirms they are zeroing in on precisely the category of high-skill knowledge work that economists predict will be most affected by advanced generative AI.
Got it. So the scope is economically relevant. The tasks are complex and digital. Let's move on to how they actually constructed and quality controlled these tasks.
Right, and what's fascinating here is how the creators ensured the reliability of the baseline. I mean, given the complexity and the potential economic sensitivity of these deliverables, the entire benchmark really hinges on the rigor used to define, construct, and ultimately grade these complex, long-horizon tasks.
Quality control seems paramount.
Absolutely. Let's delve into the expert recruitment first. These weren't just, generic contractors pulled off a platform. No. The experts were required to have a minimum of 4 years of professional experience in the specific field of the task. And the impressive part, the average experience clocked in at 14 years.
14 years on average. That's serious expertise.
It is. And this wasn't a casual process either. Recruitment involved video interviews, thorough background checks, extensive training sessions. This rigorous vetting ensures that the human expert deliverable, which serves as the gold standard baseline for comparison, truly reflects high industry standards and proficiency.
Okay, so the human baseline is solid. What about the tasks themselves?
The tasks reflect this professional commitment. Each task was designed as a complete, self-contained unit of work. It typically included a detailed request, often multiple reference files, as we mentioned.
Right, up to 38.
And resulted in a professional deliverable. And these were significant undertakings. On average, they required approximately 7 hours of dedicated work for one of these expert professionals to complete.
7 hours per task, on average.
On average. Even more telling, in the gold subset, the one used for the initial model evaluation, and that's open-sourced. The maximum reported completion time stretched up to 100 hours of effort for a single task.
100 hours. That's more than 2 full work weeks for one task.
Exactly, and that time investment translates directly into economic value. The estimated dollar value of the tasks in that gold subset averaged $398.46.
Almost $400 per task on average.
With the maximum reported value reaching an astonishing $4,114.20 for one deliverable.
Wow. So these are clearly not toy problems. They represent serious economic commitments.
Definitely not toy problems. And to guarantee this fidelity, the experts themselves rated each task. They rated difficulty, time required, and most crucially representativeness against real-world industry standards.
How did they score on representativeness?
The average score came in at an impressive 4.5 out of 5. That affirms that these highly experienced professionals felt the tasks genuinely mirrored their daily work challenges.
Okay, so the tasks are realistic and valuable. Now, the quality control pipeline. You said it was rigorous.
Iterative and multi-layered. All 1,320 tasks went through this process, receiving an average of 5 human reviews across its stages. It's really a testament to the effort required to curate a benchmark of this scale and complexity.
5 reviews per task. What did that involve? Did they use any automation?
They did integrate a model-in-the-loop screening stage, interestingly. They used OpenAI models to provide automated preliminary feedback.
For what purpose?
Mostly to flag potential issues early. Things like irrelevance to the specified owned occupation, the presence of non-digital components that shouldn't be there, or suspiciously low complexity, specifically flagging tasks that look like they could maybe be done in under 5 minutes.
A quick sanity check.
Exactly. It served as an efficiency boost for the human reviewers. But, and the paper is very clear on this, the human expert retained final, absolute authority over the task quality.
So the model feedback was just suggestion.
Purely a suggested filter. After that automated screening came the intensive, multi-stage human expert review.
The 5 stages.
On average, yes, it was broken down systematically. First, a generalist review confirmed adherence to all the standard project requirements, formatting, structure, etc.
Okay.
There, a crucial second stage review performed by an occupation-specific expert. This person rigorously assessed the task's representativeness and confirmed its feasibility. Could another expert in that field actually execute this task based on the instructions?
Makes sense.
And finally, a third stage involved a final review and an iterative feedback loop. Sometimes tasks went back and forth several times for revision, ensuring they met the benchmark's extremely high-quality standards before being included.
All right, so the tasks are well vetted. Now, evaluating the deliverables from the models. Grading these complex outputs must have been challenging. It's not just right or wrong.
Exactly. Grading required a system that went far beyond simple binary correctness. Since these are real-world work products, like, say, a marketing slide deck or a financial report grading, necessarily had to incorporate subjective factors.
Like what?
Things like document structure, professional style, adherence to format conventions, overall aesthetics, and, of course, relevance to the initial request. These matter hugely in professional work.
So how did they actually grade them?
The gold standard for grading was blinded expert pairwise comparison.
Blinded pairwise. Explain that.
Okay, so experts in the relevant occupation received the original request and the reference files. Then they got 2 or more unlabeled deliverables. One was the work product from the highly vetted human expert, and 1 or more were outputs from the AI models.
And the grader didn't know which was which.
Correct. Completely blinded. They then had to rank these deliverables based on quality, considering all those subjective factors.
That sounds incredibly time-consuming.
Extremely resource-intensive. Grading just the gold subset alone took, on average, over an hour of an expert's time per comparison.
An hour to compare 2 documents, wow.
Which leads to the next point. Given that cost and time commitment, continuous human review at scale is tough. So the authors also developed an experimental automated grader.
An AI to grade the AI's work based on the human standard.
Essentially, yes. It was trained to mimic those expert pairwise comparisons, and the results were quite promising. This automated grader achieved 65.7% agreement with the human expert grades. That's the AHA's metric.
65.7% agreement with humans. How good is that? What's the human baseline?
That's the crucial context. The human expert inter-rater agreement, meaning how often 2 different human experts agreed with each other when grading the same comparison, the AHH's metric stood at 70.8%.
Okay, so 70.8% between humans and 65.7% for the AI grader versus humans.
Exactly. Which means the automated grader's agreement rate is only about 5% lower than the agreement rate between two separate human experts. This finding suggests the experimental grader can serve as a potentially useful proxy. Faster, cheaper evaluation, particularly for high-volume testing.
But there must be caveats, right? Especially for our expert audience.
Oh, definitely. And the paper points this out clearly. The automated grader correlation was found to be lowest specifically when assessing outputs from other capable OpenAI models.
The grader favored its own kind, potentially.
It aligns with observed external evidence suggesting that models often exhibit a bias, perhaps unconsciously, toward favoring their own generations or those from similar architectures.
Right.
So relying too heavily on a proxy like this, even one with a relatively high agreement rate, risks institutionalizing that bias if it's not constantly calibrated against the human gold standard. Human review remains crucial for ultimate accuracy.
Got it. Okay. That's a deep dive into the methodology. Now for the part everyone's waiting for, the results.
Yes. Here's where it gets really interesting, connecting all that rigorous methodology to the actual performance data. Let's look at how these frontier models actually stacked up against those highly experienced human professionals performing these economically valuable tasks.
The moment of truth.
The headline results from those blind, pairwise comparisons on the gold subset. They show that models are, well, truly on the cusp of parity in some ways. Claude Opus 4.1 emerged as the top-performing model overall.
It achieved a 47.6% win rate. Now, that represents the total percentage of comparisons where the model output was ranked equal to or better than the human expert deliverable.
Wins plus ties.
Exactly, wins plus ties. And since 50% represents perfect parity.
47.6% is remarkably close.
It really is, especially considering these tasks average 7 hours of expert human effort.
That's a strong showing. What about progress over time? Are models getting better at this?
That's perhaps the most salient finding for anyone trying to forecast AI's impact. The paper analyzed the performance of OpenAI frontier models, specifically tracking from the initial GPT-4o release in mid-2024 through the projected performance of GPT-5 High in late 2025.
Okay.
And it illustrates a clear, roughly linear trajectory of capability improvement on this GDPval gold subset.
Linear improvement. That's significant.
It is. For ML researchers in our audience, this suggests that predicting when parity might be achieved across more tasks is becoming less philosophical guesswork and more a function of projecting this quantifiable linear rate of improvement.
Interesting. Did the study show different models having different strengths?
Yes, and that's fascinating too. There was a divergence in model strengths, which helps us understand where these systems are currently excelling versus struggling. The analysis suggests Claude Opus 4.1, the top performer overall, particularly demonstrated superior performance on subjective factors like aesthetics.
It's aesthetics, like how pretty the slides looked.
Essentially, yes. Things like professional document formatting, slide layout consistency, overall visual appeal. Claude seemed better at making the deliverable look good.
Okay. And GPT-5?
Conversely, GPT-5 High excelled particularly in objective accuracy. It demonstrated superior capability in meticulously following complex multi-step instructions and performing correct, validated calculations within spreadsheets or code snippets.
So Claude for style, GPT-5 for substance, maybe? Oversimplifying, of course.
That's a neat, if maybe too simple summary. It suggests if you need a beautiful presentation quickly, you might lean towards Claude. If you need flawless adherence to a strict technical specification, GPT-5 might be the current winner on accuracy.
Does this show up if you segment by the type of file being produced?
It does, yes. When we segment performance based on the deliverable file type, these differences become even clearer. Performance is highly dependent on the required output format.
Right.
While GPT-5 High leads slightly for pure text outputs like long reports or drafting emails, the win rates here actually remain generally lower than for more structured outputs.
Interesting.
In contrast, Claude demonstrated notably better performance on complex multimodal file types, specifically things like .pdf generation, .xlsx spreadsheet manipulation, and .pptx slide decks.
So that confirms its stronger visual and aesthetic abilities when generating those complex documents.
Think so. What about task complexity? Did longer tasks trip them up?
Oh, absolutely. There's a very clear inverse correlation between the model win rate and task complexity, measured by the expert completion time. Models performed best on the least time-intensive tasks.
Makes intuitive sense.
For tasks requiring only 0.2 hours of human expert effort, Claude achieved an impressive 56% win plus fast rate. That's actually slightly exceeding human parity for the simplest tier of work.
Wow, better than the expert on the quick stuff.
In aggregate, yes. However, as complexity increases, the models struggle significantly more. Tasks requiring 8 or more hours of expert time saw the model win rate drop substantially, bottoming out at 37% for Claude on those really long tasks.
So down from 56% to 37% as tasks get longer.
Right. It confirms that long-horizon, complex knowledge work, the tasks demanding the deepest sustained effort and integration, remain the most challenging barrier for current AI systems.
And I assume performance varied by economic sector too.
Yes, the sector variation is equally broad. Models approach parity in certain sectors, specifically government, retail trade, and wholesale trade.
Any idea why those sectors?
Well, the paper suggests the knowledge work in these areas might be more standardized, perhaps less complex intrinsically, or maybe relies less on deep proprietary tacit knowledge compared to others.
Okay. And where did they struggle most?
Conversely, sectors involving highly specialized roles, think certain advanced finance functions or complex engineering roles, which are detailed extensively in Figure 11 of the source paper, consistently showed the lowest win rates across all models tested.
So high-end specialized human expertise still holds a substantial lead in those domains.
For now, yes, the data confirms that quite clearly. Okay, so if we connect this performance quality back to the bigger picture, the true economic value proposition of these models comes not just from what they can do qualitatively, but from efficiency, right? How fast and how cheaply they can do it.
The dollars and cents argument.
Exactly. And the paper moves beyond just qualitative assessment by providing a really rigorous quantitative analysis of potential speed and cost benefits. But it does so under specific practical workflow assumptions.
Right. Assumptions matter hugely in economic modeling. So, to understand this, we need to clearly define the variables they use for the calculation. This is crucial for our expert audience.
Let's lay them out. First, $. That's the human expert professional completion time. On the gold subset, this averaged 404 minutes, so about 7 hours.
Okay, 7 hours human time.
Then $, the associated human expert completion cost. This averaged $361 for those 7 hours of work.
Got it.
Next is R dollars, the human expert professional review time. This is the time needed for an expert to carefully review a model-generated deliverable. This averaged 109 minutes.
Almost 2 hours just to review the AI's work.
On average, yes. It's a crucial cost component, often underestimated. Then you have $, M&E, the model completion time and cost. For today's frontier LLMs, these are typically negligible fractions of a cent in seconds or minutes.
Okay.
And finally, $, the model win rate versus the human expert, that 47.6% for Claude Opus 4.1 we discussed.
All right, so those are the inputs. What was the workflow model they used?
They modeled efficiency gains under what they call the try n times then fix it workflow.
Try n times, then fix it.
Yeah, it's a practical approach that acknowledges the model isn't perfect yet. It calculates the expected time, ETII, by simulating another rounds of the model trying the task, MTI, followed immediately by expert review. If, after null attempts, the model still hasn't produced an acceptable output based on the win rate dollar, then the human professional has to step in and complete the entire task from scratch.
Okay, so you give the model n shots, checking each one before giving up and doing it yourself.
Precisely. The mathematical expression for this expected time ETIII is key to understanding the logic. It's given as MTI plus RTI plus 1Y and HTII.
Okay, let's break that formula down a bit for clarity.
Sure. The first term, the one involving the cumulative time MTI plus RTI, that basically calculates the expected cost of the iterative process. It's the time spent trying the model other times and reviewing those nullers outputs.
And that fraction part, frac 1.
That represents the expected number of attempts you'll need to make before achieving success, statistically speaking, given the model's win rate, $. If the win rate is high, you expect fewer attempts. If it's low, you expect more attempts.
Okay, that makes sense. So that's the expected cost of trying and reviewing. What's the second term?
The second term, $1Y, HT$, that's the cost of failure. The part $1Y is the probability that the model fails all nuller times in a row.
Right. $1Y is the failure rate raised to the power of a nuller tens.
Exactly. And if it fails null hours, you multiply that probability by the full human completion time, HDI, because the human has to step in and do the whole thing unaided. It mathematically captures the trade-off, the cumulative cost of trying reviewing versus the diminishing probability you have to revert to full human effort.
Okay, that's a clever way to model it. So, applying this rigorous workflow model, what were the results? What were the potential efficiency gains?
The economic benefits for the top-performing models, even with that significant review time cost baked in, are substantial. For GPT-5 High, running the simulation under the Trinix, then fix-it setup showed a potential 1.39x speed improvement.
So nearly 40% faster overall task completion time.
Yes, compared to the professional completing the task entirely unaided. And the cost improvement was even more significant, a 1.63x cost improvement.
Over 60% cheaper.
Potentially, yes, under this specific model.
Now, this speed and cost analysis, it sounds promising, but you mentioned caveats. What should our expert audience keep in mind?
Right, a couple of important ones. First, the modeling doesn't fully capture the potential, often disproportionate cost of catastrophic mistakes.
Meaning?
Meaning, if the AI makes a really bad error that isn't caught in review or requires significant human effort just to undo the damage before starting over, that extra cost isn't explicitly modeled here.
Okay, fair point.
Furthermore, the model makes a simplifying assumption that the human expert, when performing the task entirely unaided, spends zero time reviewing their own work.
Which is unrealistic, right? Professionals review their work.
Of course. In reality, experts spend time self-correcting and reviewing. So if you were to incorporate the expert's self-review time into the baseline $, the relative efficiency benefit of the AI assistance would likely look even better than the 1.39x speedup suggests.
Interesting. Okay, let's shift from efficiency to failures. Understanding why models lose these comparisons is just as important as knowing how often they lose.
Absolutely. The failure analysis rigorously categorized the reasons experts provided when they preferred the human deliverables over the models. And the prevalence of failure modes is quite revealing.
What was the biggest reason models failed?
For Claude Opus 4.1, Grok 4, and Gemini 2.5 Pro, the primary reason for rejection, the most common failure category, was instruction following.
Instruction following, that sounds big.
It's almost counterintuitive, isn't it? Here we have these incredibly powerful models capable of complex multimodal reasoning, yet their main stumbling block is often the mundane. Failing to deliver all the requested files, ignoring critical reference data that was clearly stipulated in the prompt, or just missing a required step in a checklist provided.
How common was this?
For Grok 4 and Gemini 2.5 Pro, instruction following failures accounted for a massive 35% and 40% of their total losses, respectively.
40% of losses just from not following instructions. Wow.
It's significant. Interestingly, GPOE5 High, which we noted excelled at accuracy, actually demonstrated superior instruction following compared to the others. It had fewer losses in that category.
So what was its main failure mode then?
GPT-5 High lost primarily due to formatting errors.
Formatting, like the aesthetics Claude was good at?
Exactly. Aesthetic or structural mistakes in the final deliverable. Things like inconsistent fonts, awkward layouts in slides or documents, improperly structured tables. This suggests that while GPT-5 could follow the technical requirements of the task better, the visual and structural quality control remained a significant bottleneck for it.
And across the board, how often were pure accuracy failures the cause? Like hallucinations or wrong calculations?
That was relatively rare. Models showed the fewest losses categorized as pure accuracy failures. This implies that the failure is often one of rigorous execution and adherence to constraints, rather than a fundamental inability to reason correctly about the core task.
Okay, so they usually know what to do, but struggle with how to present it perfectly or follow every single constraint. Now, how severe were these failures typically?
That failure data is given crucial weight by the severity analysis. They did a deeper dive specifically into GPT-5 High failures. It showed that when the model lost, the output was rarely catastrophic.
What were the common severity ratings?
47.7% of its failures were rated acceptable but subpar, meaning the expert could probably use the output, maybe with some edits, but it was aesthetically or stylistically inferior to what they'd produced themselves. Another 26.7% were rated bad, meaning not fit for use without major revision, but still not actively dangerous or harmful.
And the really bad ones? Catastrophic failures.
Critically, only 2.7% of all observed failures for GPT-5 High were rated catastrophic, which they defined as harmful or dangerously wrong.
Less than 3% were truly dangerous.
Yes. This low rate of high-impact failure is essential for making that try in times, then fix its workflow actually viable in practice. It suggests the vast majority of that human review time, the $12 hours, is spent correcting minor to moderate issues, not constantly mitigating disaster.
That's reassuring. So this analysis must inform how we can improve performance, right? What levers did the study identify?
It tested two main approaches. First, somewhat obviously, reasoning effort.
Just making the model think harder.
Pretty much. Running models like O3 and GPT-5 at high reasoning effort, which often translates to increased computation, maybe more internal steps in the thought process, consistently improve performance compared to running them at low or medium effort settings.
Any specific numbers?
Yeah, for example, GPT-5 High achieved that 38.8% wins plus ties rate at high effort. That was a substantial gain up from just 32.7% when run at low effort. So more compute helps.
Okay, more effort helps. What was the second lever?
This one was perhaps more surprising in its impact. Scaffolding and prompt tuning?
Prompt engineering, essentially.
Yes, but maybe more structured than just fiddling with words. The authors utilized a general prompt that encouraged the AI system executing the task to perform rigorous self-checks before outputting the final deliverable.
What kind of self-checks?
For instance, instructing it to render files as images internally, to check the layout visually, explicitly telling it to avoid special characters that might break formatting, reminding it to be concise. Basic quality control instructions, really.
And did this simple scaffolding work?
It yielded immediate and massive gains. This general prompt tuning improved GPT-5 High's win rate by 5 percentage points, jumping from that 38.8% at high effort up to 43.1%.
Just from adding self-check instructions?
Primarily, yes. And what's truly telling is the mechanism behind that gain. The paper tracked how often the agent used its multimodal capabilities, like rendering images, to inspect its own deliverables before submitting them.
Okay.
Before the prompt tuning, the agent only did this kind of self-inspection 15% of the time.
Huh.
After adding the prompt tuning, that usage skyrocketed to 97%.
Wow. From 15% to 97% self-checking.
Exactly. The model apparently had the capability all along, but it required explicit, relatively simple scaffolding in the prompt to enforce the necessary quality control and self-critique loop consistently.
That's a huge takeaway. It's not always about fundamental model power, but also about guiding its process.
Precisely. Finally, they ran one more experiment called under-contextualized GDPval, which exposed a critical real-world limitation.
What did they do?
They deliberately took some tasks and made them underspecified. They removed details about where to find necessary input data, or failed to clearly specify the required output formatting, things that might happen in a real messy request.
And the result?
Model performance significantly degraded. It demonstrates that while models are getting excellent at solving precisely specified problems, they still struggle quite a bit with that initial messy professional task of figuring out the full context, asking clarifying questions, which they couldn't do here, and resolving task ambiguity things humans handle much more naturally through interaction.
That makes perfect sense. Okay, really insightful findings on performance and failures. Let's talk limitations and wrap up. So we've covered the impressive scope, the rigorous methodology, the promising results, and the key failure modes. But what does this all mean for the immediate application of these models? Before we draw final conclusions, we really must acknowledge the current boundaries and limitations of the GDPval benchmark, at least in this initial version.
Absolutely. Context is crucial. No benchmark is perfect or complete.
The primary limitation seems to be scale, right? While it's comprehensive in its approach to sectors and task types, the initial dataset size is still limited.
That's right. It covers only 44 occupations, with 30 tasks per occupation. The authors themselves acknowledge this is a robust initial cut, a great starting point, but it's certainly not a comprehensive evaluation of the totality of digital knowledge work across the entire U.S. economy. There's much more work to potentially cover.
Okay, so dataset size is one limit. What about the scope of the work itself?
The scope is also strictly limited. It focuses specifically on self-contained digital knowledge work tasks, the kind performed solely on a computer by an individual.
Which means exclusions are important. What's not covered?
The exclusions are significant. Obviously, manual labor, any task requiring physical interaction with the world. Also, tasks that rely heavily on extensive tacit knowledge that hard to articulate know-how or proprietary company knowledge. Tasks needing access to personally identifiable information, PII, or specific proprietary software tools were also excluded for practical reasons. And, critically, the benchmark doesn't cover tasks that are fundamentally reliant on complex, synchronous communication or interactivity between individuals. Collaboration isn't measured here.
And that leads directly to the third limitation you touched on earlier. The tasks are precisely specified and one shot.
Exactly. They reflect the ideal scenario where someone gives the AI a perfectly defined assignment with all necessary context up front.
Which isn't always reality.
Rarely, right. They don't simulate that real-world iterative effort where a significant portion of a professional's time is spent just figuring out the full context, clarifying requirements, refining the prompt, and handling ambiguity, often through back-and-forth communication. The current version lacks that interactive element inherent in so much high-value professional labor.
Good point. Despite these limitations, the authors are making parts of this available.
Yes, to ensure the longevity and utility of this work, they've committed to open sourcing key components. Specifically, the prompts and reference files for that 220 task gold subset we've been discussing are publicly available.
Which should facilitate future research and allow others to benchmark their models against this standard.
Precisely. It allows for replication and extension.
And what about the automated grader?
Additionally, that experimental automated grader we discussed is publicly accessible. You can find it at the evils.openai.com domain.
So people can try it out?
They can. However, the authors strongly emphasize, again, that due to the cost, the inherent difficulty, and the potential biases in grading complex, subjective outputs automatically, the blinded human expert comparison remains the recommended gold standard method for truly accurate evaluation. The auto-grader is a useful tool, but not a replacement for human judgment yet.
Understood. So let's try to summarize the key contributions here for you, our expert listener.
Well, I think the creation of GDPval provides the industry with a genuinely new, economically weighted data set. It really attempts to move model evaluation out of the purely academic lab and into the context of professional work.
Right.
The study delivers clear capability benchmarking across quality, but also, importantly, speed and cost under that defined workflow. It gives us quantitative estimates.
And the failure analysis.
And that rigorous analysis of how performance can be significantly shifted by levers like reasoning effort and maybe surprisingly meticulous prompt tuning and scaffolding. That insight about self-critique is huge.
Agreed.
And finally, by open sourcing the gold subset and the grader, the paper establishes a clear, attributable leading indicator of AI's economic relevance that really does transcend those more abstract academic benchmarks.
So pulling it all together, this study provides a really quantifiable view of where frontier models stand today. They're not quite at expert parity across the board, especially on complex tasks or in specialized domains.
No.
But they're offering compelling and measurable efficiency gains. That 1.39x speed improvement, 1.63x cost saving, when integrated carefully into a human-supervised workflow. And interestingly, the main barrier to parity right now seems less about a lack of fundamental reasoning power.
And more about the lack of consistent, rigorous self-critique and adherence to specifications, the instruction following and formatting issues.
Exactly. Which leads us to our final provocative thought for you, our listener, to consider. GDPval clearly reveals that these main barriers to reaching human parity are often quite mundane. Instruction following errors, aesthetic formatting mistakes, given the demonstrated linear progress and fundamental capability we saw in Figure 6.
That steady upward trend.
And given the massive performance gains achieved through relatively simple prompt tuning, designed specifically to enforce those aesthetic checks and self-critique loops, remember jumping from 15% to 97% self-review.
A huge jump from simple prompting.
How rapidly do you think those formatting and instruction following failures, which seem to be the primary remaining drag on efficiency and win rates, will actually be engineered out of these systems? And if, or perhaps when, they are largely engineered out, will that human review time, the $20, which currently averages almost 2 hours, become so negligible that the current cost equations, $63 player savings, are dramatically undercut? Could this lead to an even faster acceleration of AI's economic impact than even this quite bullish paper currently forecasts? Something to think about.